Hi everybody. Well, thank you. Thank you for the introduction, and thank you all for being here. Yes, today I'm going to talk about a neurogeometric model for stereo vision, which actually ties together the functional architecture at the basis of binocular cortical mechanisms with psychophysical experiments through their mathematical formalization using instruments of differential geometry. The ultimate goal would be the one to identify 3D percepts that characterize the three-dimensional visual scene. Okay, it works. I'm sorry. Okay. Yeah, well, let's start from the beginning. I mean, binocular vision involves the use of both eyes to encode three-dimensional information of the visual scene, information that we have supposed to be projected on parallel retinas. Well, actually, the visual system is able, starting from this two bidimensional projection, to reconstruct the three-dimensionality, and the main challenge is to determine the correct matching among all these possibilities, since they can give rise, they can generate different distal stimuli. In literature, the problem of determining the correct matching usually goes under the name of stereo correspondence. Well, the formalization of this problem involves classical triangulation instruments, and in particular, we have dealt with perspective projections through optical centers on two parallel retinas. And we have just said that the main issue is to couple corresponding points in the left and right retinal planes, which we can call QL and QR, in order to project them back into the environment space and obtain a three-dimensional point Q. How? Well, the horizontal separation of the eyes causes these two retinal projections to be slightly different. These differences are usually called disparities, for example, horizontal positional disparity. And disparities are actually the main clue for 3D visual perception. Well, besides horizontal positional disparity, we can also find orientation differences if, for example, we consider the projection, the bidimensional projection of an oriented edge in R3. Well, these edges are usually thought to be tangents to visual stimuli, and here geometric computation on curve matching has been developed in order to infer the three-dimensionality of the visual scene, for example, by Fougera. And in this setting, the Zucker group was able to derive the 3D Frene frames of a space curve, starting from differential information on the two retinas. Moreover, they were able to solve the stereo correspondence, basically transporting these Frene frames along suitable curves that are helices whose spirals develops in that, basically defining a geometric measure in order to describe the compatibility between corresponding points. Yeah. Although this measure relies on a purely geometric approach, this model is actually neural-based, since their starting point is the differential information on the two retinas, which is actually encoded by receptive profiles of monocular simple cells in the primary visual cortex. We have already seen, for example, in the first talk, that monocular simple cells are selective for orientation, where we stress again that orientation is identified with tangents to the visual stimulus. Their response to a visual signal is quantified and modeled in terms of Gabor functions. And what's interesting for us is that the primary visual cortex is actually the first area for processing the binocular signal. And Anzai, Ozawa, and Freeman found that binocular simple cells actually perform a nonlinear integration of these two left and right monocular responses. So we know that the behavior and the functional architecture of monocular simple cells has been modeled using instruments of sub-Riemannian geometry, for example, in the work of Petitot and Tondu and Cinti-Sarti, and we have already seen that. In particular, the action of the cell is to lift the bidimensional stimulus, the visual stimulus, in the space of position and orientation, assigning for each position its orientation. So we have a lifting in the space R2 times S1. And this action induces the choice of a contact form, and in particular, visual signal has been modeled to propagate along integral curves of vector fields that lie in the kernel of this form. We have already seen an example of these integral curves, and it's shown here together with their bidimensional projection. Well, The idea for binocular vision was to generalize this bidimensional model to the three-dimensional case. And we started with monocular information on the two retinas, and we see how it is possible to lift this in the space of 3D position and orientation R3 times S2. For three-dimensional points, they can be recovered, basically inverting perspective projections. And what about tangents? If we start from monocular one form on the two retinal planes, we can extend them in the three-dimensional space, and then we can take their wedge product. This defines a two-form that, using the Hodge duality, can be seen as identifying a direction which encodes the tangents to the three-dimensional visual stimulus. So this result actually falls in the classical literature of curve matching, but we were able to connect it with the neural results proposed by Anzai, Ozawa, and Freeman, since these two forms can be seen as embodying the nonlinear integration of the left and right monocular structures. So this induced the following choice for the considered vector field. We'll take the vector field YR3, which is the one that encodes the tangents to the visual stimulus, and then we'll consider orientation y theta and y phi, which are vector fields regarding the orientational variables. These vector fields can be seen as a restriction of a section of the left invariant vector fields defining the group of rigid body motion in 3D, which naturally couples position and orientation, as studied by Duitz and Franken. And moreover, for these vector fields, it holds the Romander condition. This means that we can span the tangent space considering this triple and its commutators. Since Romander condition holds, we are actually able to connect every pair of points considering integral curves. In particular, we choose to consider a very special case of integral curves, namely constant coefficient integral curves, where we set the coefficient above the vector field YR3 to be equal to 1, since it represents the tangents of the stimulus and it never vanishes, while we take C1 and C2 to be real elements. An example of the curves varying C1 and C2 can be found in the figure superimposed on the three-dimensional stimulus. And we notice that among our curves, we can retrieve different families. For example, if we restrict ourselves onto frontoparallel planes, which are planes that are parallel to our parallel retinas, we can recover arc of circles, and this is in accordance with the previous sub-Riemannian model for monocular vision proposed by Citti and Sarti. And moreover, we can also recover helices whose spirals develop in depth in accordance with the stereo model proposed by Zucker. Well, to us, these curves are important because they are thought to be at the basis of the Gestalt law of good continuation. This is one of the laws governing the formation of visual percepts, and in particular, it states that elements aligned in space tend to be seen as belonging to the same perceptual unit. We have already seen that, the visual system is thought to encode this principle thanks to how the visual system encodes this principle has been theorized by Field, Ice, and Dess by the introduction of the concept of association field based on psychophysical experiments. And in particular, we have already seen what association field is. This is basically a pattern that describes if two elements can be seen as belonging to the same perceptual unit in terms of position and orientation. In particular, they found that the correlation between oriented elements was stronger if these were aligned or co-circular, and they proposed a set of curves to model this association, curves that are formalized, for example, by the sub-Riemannian integral curves of the model proposed by Citti and Sarti, or another model, which we have already seen, is to consider geodesic of the same sub-Riemannian structure. Okay, in the three-dimensional case, the curves that are suitable to describe association between oriented elements have been studied using psychophysical experiments. And in particular, they are required to be smooth, They are required to satisfy the geometry of 3D relatability, which is actually the transposition to the three-dimensional case of alignment and co-circularity. And moreover, they are required to satisfy the coplanarity constraints. This means that the strength of the correlation on coplanar planes with initial edge must satisfy the bidimensional constraints of bidimensional association fields. So we choose to model the association underlying this 3D perceptual organization using integral curves of our chosen vector fields. Since they are smooth, they connect 3D relatable edges and they locally satisfy the coplanarity constraints. Then we can use these curves to identify 3D percepts. How? Well, the first step, according to previous work of Sanguinetti, Citti and Sarti, or Barbieri, Cocci, Citti and Sarti, the first step is to consider the stochastic counterpart of these 3D association fields. In particular, we have considered the following stochastic differential equation, which is characterized by a drift term in the spatial variables and diffusion in the orientational ones. In particular, we are interested in the time-integrated probability density of this stochastic process, namely J lambda, which can be seen as a fundamental solution for the forward Kolmogorov operator that can be written in terms of the chosen vector field. We choose to approximate this solution using a Monte Carlo method, and the results are displayed in this figure, where we shown an isosurface for this kernel restricted in the three-dimensional space. I mean, this kernel describes the probability of interaction between oriented elements, and in particular, it encodes 3D geometric position orientation information. So we can insert it in as a facilitator pattern in the mean field equation describing the evolution of the neural population activity. So the propagation of the activity along the connectivity generated by the visual scene can be described in terms of this integral differential equation, where A is the neural population activity, J is a symmetric version of our kernel, sigma is the transfer function, C is the feed-forward input, and omega is the sect activated by the visual stimulus. And if we generalize stability analysis, for example, used by Breslov and Cowan for study visual hallucination, or used by Sarti and Citti for studying the emergence of bidimensional percepts, since in a neighborhood of a stationary state the equation becomes linear, we know that stability analysis translates into an eigenvalue problem. Well, this in the continuous case, but in application we usually work with a finite number of points, and so to the kernel J it is usually associated an affinity matrix A, and in particular the eigenvalue problem becomes a problem of diagonalization of the affinity matrix. Here, spectral analysis on this affinity matrix translates into the identification of 3D percepts, and more precisely, eigenvectors will be related to percepts and eigenvalues to their saliency. This has been shown in the bidimensional case for the emergence of bidimensional percept by Sarti and Citti, and this work is linked with spectral clustering and dimensionality reduction results of Perona and Freeman. So, I will conclude with some examples in order to illustrate these ideas. And yes, the first one is to start with a couple of retinal images, and we couple corresponding points in the left and right images, and we lift the stimulus in this three-dimensional space of position and orientation. Of course, we recover the three-dimensional curve, but also we generate some noise due to the false matching on the left and right retinal planes, since we are coupling points which share the same y coordinate. This is because we are considering projection on parallel planes. The ultimate goal will be to select the points belonging to the 3D curve. So we compute the affinity matrix, we diagonalize it, and we display the eigenvalues. And then we select the eigenvectors associated to the largest eigenvalues, using them to segment the visual scene in a cluster. In particular, in this example, we notice that there is only one main cluster describing the visual scene, and in particular, the points selected by the eigenvector are the one that belongs to the 3D curve. So basically we are solving the stereo correspondence, and at the same time we are performing segmentation. This maybe is more clear in the second example when we consider a couple of images displaying tweaks. Since our starting point is position and orientation on the two retinas, we have to Gabor filter these images, basically mimicking, if you want, the behavior of monocular simple cells. Then we reapply the same algorithm as before, and in this case we notice that there are two main clusters describing the visual scene, each corresponding to one of the two tweaks. So we can conclude that the introduction of our neurogeometric model for stereo vision allows to simultaneously solve the corresponding problem, but also to segment the visual scene, since we are able to identify the 3D percept that characterize it. And yes, thank you, I'm finished, and thank you all again for your attention.
Thank you for the nice talk. Let's see, are there questions in the audience? Because there's still a few minutes left, I see. Okay, then I would like to ask a question you mentioned that for the association fields in 3D, we need to go to the embedding in the Lie group SE3 and then look at the Lie group quotient, and then we have to take a section. And I think because we studied these the exact formulas of these forward Kolmogorov equations and compared it to approximations, we realized that we had to take the section alpha is minus gamma rather than alpha 0 if I use the Euler angles alpha, beta, gamma for the rotation matrices. Have you looked at this, and is there a serious difference in practice, or didn't it really matter in the experiments at the end?
I mean, for the final experiments, there is no difference. I mean, because the kernel that we get at the end with, I mean, this is the section that corresponds to alpha equal to 0, yeah, actually, and yes. So for the experiments at the end, there should be there is no difference. The kernel we simulated are almost the same. They have the same shape, and the error between the two of them is very little. Yeah. But
basically the fact that because for alphas minus gamma you have 0 torsion, and for alpha 0 you still have a little bit of torsion, but it's very little. And the coplanarity is hardly violated in the exact or in the numerical Green's functions that you use.
But the real difference in taking the other section, I mean alpha minus gamma, is here. I mean in the definition of the vector fields. And it's true that when you take that section, you have torsion equal to 0, for example, but I mean, we don't really want torsion equal to 0 because we want at the end to retrieve ellipses. And if we have torsion equal to 0, we would have just arc of circles in order to describe, for example, these curves or the compatibility between the connection of points. I mean, if we consider just curves with the torsion equal to 0, it means that we are coupling points that lie just on the plane, just on a planar planes in 3D.
Yeah, but I want to, if alpha is minus gamma, then if two local orientations are coplanar, if they are coplanar, they will be connected with a coplanar
if they are
exponential curve. But if they're not, they're not. Then alpha minus gamma will not give you these.
Yes, exactly.
So they would do the right thing if it is coplanar. So
yes, if they are coplanar. Yes, I mean, if they are coplanar, you should take an arc of circle and you couple them with that. But if they are not, and that's the point. I mean,
then you get different. Different connecting curves. Yes.
So at the end, I think we are.
But in practice, it didn't matter much, I guess. No, I would expect that. Yeah. Okay. I think because of time, we have to continue with the next speaker. Are there maybe very short questions still? Because I didn't see a question from the audience yet. Okay. Yeah.
Oh no. Sorry.
Yeah. Go ahead, Barbara.
Can we go further? You talked about curve. Can we also do surfaces.
surfaces.
Yes. How is it for?
I don't know. I mean,
Is it possible to develop your context in this?
maybe it's possible because here we are characterizing everything in terms of a form, two forms. So maybe we can extend this approach in considering something that grasps something more than just a contour, but a surface.
And
For
then you
example.
will have some integrability condition to
Yeah, but we never really think about it for the moment, at least. But yes.
But probably the visual systems do something like this because
Yeah.
we want to reconstruct surfaces, so integrable 3D objects.
Yes. Thank you very much.
Okay, then I propose we go to the next speaker. First, thank the speaker for excellent talk.